Okay, so this is 3.2, and this is linear functions. So we're going to continue on with these functions, and they are going to be specifically today linear functions. Remember, a function definition is every input has exactly one output. A linear function in two variables. Those two variables, as you can imagine, when I'm talking, are going to be x and y for the most part. And again, if we have a function, I could have something like, I could have the hours a mechanic works as my x and maybe the cost that it's going to end up costing me as my y. Point being, we have our dependent variable, which is our x, and our independent variable, which is our y. A linear function in two variables, x and y, is an equation that can be written as y equals mx plus b. And hopefully, I actually talking to the in-person kids here, this is something that we might not have gotten to totally last year, introduced to it, but this is slope-intercept form of a line. Y equals mx plus b, slope-intercept form of a line. If I can get an equation, manipulate it to solve for y and get y by itself, and it looks like this, I have some x with some coefficient in front of it, and I could have some number off the back plus or minus it. I don't necessarily need that b there. It could be plus 0, which we wouldn't write. But if I can manipulate that equation to look like that, it's a line. The graph of a linear equation, the graph of a linear equation is a line. It's not rocket science. Linear means line. When I graph them in a coordinate plane, they make a line. But we're going to have to clear something up here though. A linear function, remember, a function, every input must have one output. So I will tell you, graphs of linear functions, graph of a linear equation I wrote, or a linear function, is a line, except when I have a vertical line, a non-vertical line. That's going to be a function. And if I think about it, it should make sense. If I have a line that looks like this, and I ask if this is a function, hopefully you would do vertical line test and say, yes, this is a function, and hopefully it is a line as well. Now remember, if I have a line x equals something, I have a vertical line. That would not be a function. It's linear, it's a line, but it's not a linear function. It's not a function because here if I have the line x equals a vertical line, all your inputs, all your x values are the same. So the graph of a linear function is a line, but it's got to be a non-vertical line. Can't be straight up and down, that's not a function. Linear functions, and this is a key takeaway, linear functions have a constant rate of change. And when we're talking about a line, hopefully you remember this, we're talking about slope. Rate of change is slope. We're going to start introducing in some vocab. It's going to take us forward. Nonlinear functions do not. They do not have a constant rate of change. And when you graph that, its graph is not a line. It's as easy as that. When I look at it in a graph, it ain't making a line. Little XY coordinate plane. Have a graph that maybe looks like this. It's certainly a function because it passes the vertical line test, but is it linear? No. It's nonlinear. Why is it nonlinear? Because it ain't a line. It's a U. It doesn't have a constant rate of change. It's curved. The rate of change is ever changing. It is not consistent. It's not constant. It's not changing by the same amount every value of x. Versus if I make this little coordinate plane, that is indeed linear. And why? Because it makes a line. It's as simple as that. This has a constant rate of change. This has slope. You are rising and running at the same rate. Constant rate of change. I want to go back to this idea right here of y equals mx plus b. In your homework in this section, it asks, just by looking at the equation, can I tell if something is a linear function? And if we can get it to look like y equals mx plus b, then it is. This y has to be to the first power, this x has to be to the first power. So if I have something that is y equals x squared, let's say, does that look like y equals mx plus b? Well, no. My exponent on my x is 1. This is 2. That's squared. This is nonlinear. I could have something like this. 1/2 xy. Ask you if that is linear. Well, y is by itself, but I should have some constant, some number in just x, and I have x times y. This is not linear. It doesn't look like, I can't manipulate this equation and get it to look like y equals mx plus b. If you have something like this, y equals 3x plus 4, is that linear? It is. It looks like y equals mx plus b. You need to be able to recognize looking at these equations and tell me if it's a line or not. If you have something that looks like this, 3x minus 2y is equal to 8. Is that linear? Well, it doesn't look linear now, but I just got to start making some comparisons. This y is to the first power, this x is to the first power, and I've got some constant right here. Couldn't I easily solve that for y? I could subtract 3x, negative 2y is equal to negative 3x plus 8, and I could divide everything by negative 2. I don't even really care what this comes out to right now. I just know that I have a function that now looks like y equals mx plus b, and it's linear. If you're given an equation, see if you can make it look like y equals mx plus b. That will tell you it's linear. If you're given a graph, look at it. Does it make a line? If it is a line, it's linear. We're going to go back to that constant rate of change. And your question is, again, is this linear or nonlinear? Does it make a line or doesn't it? And here we're going to be given some values of x and y in a table, an input-output table. I've got an x, I've got a domain, I've got an independent variable, I've got a y, I've got a range, I've got a dependent variable, I have an output, I've got an input of x, an output of y, all those different names. 3, 6, 9, 12, 36, 30, 24, 18. And the question is this linear? We've got to look at our rate of change. And when you're talking about rate of change, you're talking about a common difference. How do I get from one to the next? What is the difference here? How do I get from 3 to 6? Well, I add 3. How do I get from 6 to 9? I add 3. How do I get from 9 to 12? I add 3. This is a constant rate of change. My x is changing by 3s. If my y's are changing at a constant rate, then this will indeed be linear because I will have a constant rate of change in my x and my y. And I can see to go from 36 to 30, I subtract 6. 30 to 24, I subtract 6. 24 to 18, I subtract 6. My rate of change in my x and my y are consistent within each other. I have a constant rate of change. This isn't linear. And the reason is constant rate of change. X is going up by the same amount, y is decreasing by the same amount. As long as this constant between the y's and constant between the x's, I have a linear function. Here's another xy. And I'm going to make my x's 0, 1, 2, and 3. 3, 5, 7, 9. Is it linear? Well, I'm adding 1. I'm adding 1 to get to 1 to 2. From 2 to 3, I add 1. This rate of change is constant. 3 to 5, I add 2. 5 to 7, I add 2. 7 to 9, I add 2. It's constant in my x, it's constant in my y's. Yes, this is linear. And your reason is it has a constant rate of change. One more. One, 2, 3, 4, 2, 4, 8, 16. Again, the question is this linear or nonlinear function? Well, my rate of change in my x, I'm adding 1, plus 1, plus 1. Has to be constant. This couldn't be a 5. If this was a 5, my rate of change here would be a 2. I would have a 1, and 2. That wouldn't be constant. They're all constant. They're all the same. Be very careful on your y's. There's a definite pattern. Hopefully you're picking up on the pattern. 2 to 4, I multiply by 2. 4 to 8, I multiply by 2. 8 to 16, I multiply by 2. I'm taking this y and I'm doubling it. But when I look at my rate of change, remember that common difference, the addition or subtraction, to get from 2 to 4, I add 2. To get from 4 to 8, I add 4. To get from 8 to 16, I add 8. This rate of change is not constant. I agree 100%. There's a pattern here. This is what we call geometric. This is an exponential graph. This is something that if I graphed it, it would start out slow and then it would get really fast and really steep really quick. Because look, if I'm at 4 here and I go to 5, this is going to double, it'd be 32. At 6, it's going to be 64. This is going to get real steep real fast. That's not a line. How do I know though? I check for the rate of change. And remember, it's a common difference. It's the addition or subtraction of it. When this turns to multiplication, there's a pattern and you can graph it, but it ain't no line. Last thing we have to look at here, another definition. A solution of a linear equation in two variables. So you're going to have an x and a y, an independent and a dependent variable, is an ordered pair. And an ordered pair, remember, is an x and a y. That's what I'm talking about with an ordered pair. Sometimes the points are distinct. Vocab word. They're distinct. They'll stand alone. Sometimes they connect. And how do we know if they're going to stand alone and be distinct or they're going to connect? Well, the problem is going to tell us, or it's going to give us hints on whether we should connect them or not. And we do that by looking at the domain or the x's. I'm going to look at this little concept right here, though. This ordered pair being a solution to it. So here's back to our function. If I have this right here, this is our table. Let's say it's 3x plus 1. This is back to input output, our little function box. Right? I had my function box, and x went in, I had my function right there, and then a y came out. We're going to choose some values for x here. What's an easy one to choose? Well, if x is 0, I plug in 0, that would go away, y would be 1. 3 times 0 plus 1 gives me 1. I have the ordered pair 0, 1. If I went 1, it would be 3 times 1 plus 1. Well, that'd be 3 plus 1, which is 4. You have the ordered pair 1, 4. Hopefully you can see a pattern picking up. If this is going up by 1, this is going up by 3s. This should be 7. 3 times 2 is 6, plus 1 is indeed 7. You have the ordered pair 2, 7. Now you could plot these, and you would get a line. Why are these ordered pair solutions? Because I can plug them right back in. When we were doing chapter 1 and you got an equation right or wrong and you said, Mr. DeLong, I don't know if this is right, I would tell you, well, you better check it. You better plug it back in. So if I take this 2, 7, this xy, and plug it into my function, 7 would equal 3 times 2 plus 1. My y went here, my x went there in that function. Now I'm just going to do the math. 6 plus 1, and I've already done it because I got it. 7 equals 7, it checks. When that checks, I know that that point lies on the line. The solutions are ordered pairs. We're going to get in a ton more of this as we go forward. That's the first part of the statement. Sometimes the points are distinct, sometimes they connect. This is the idea we introduced in 3.1 of discrete and continuous data. We'll do discrete first. Discrete is a set of input that consists of only certain numbers in an interval. A set of input, a set of x's, a domain that consists of only certain numbers in an interval. Continuous data is a set of inputs, a set of input, a set of x's, a domain, an independent variable that consists of all numbers in an interval. Here's what discrete looks like. If I just take a simple number line, it's a set of input that consists of only certain numbers. If I put these values on a number line, I'll say that's -1, 0, 1, 2, I'll stop at 3. They are not connected. They are individual points. They're individual points on that number line. If you were to look at these in your graph, these are your inputs, these are your domain, your graph would look something like this. I don't even care what my y's are, I'm going to be looking at my x's. But you would have something that may look like this. It's just a series or a set of data points. There's no line connecting to them. The discrete data is going to be dictated by what that x is. Maybe x is the number of tickets. Well, I could have, this data point wouldn't make sense. If it's a numbered ticket, I could have 0 tickets, 1 tickets, 2 tickets, but I can't have 1.5 tickets. These aren't connected because this x is not part of the problem. It's discrete. These stand alone versus something that's continuous. And I'm going to use the same number line because when we were describing domain and range, and that data was continuous, we used an interval. This is saying that I want inputs or domain that is between -1 and 3. And this includes every number between it. It could be 1.1, 1.11, 1.112. It includes every one. This one is 1 only, 2 only. There's no line connecting. It's not including the numbers between 1 and 2. This includes everything, continuous data. Those are graphs that are connected. So if I make a little XY coordinate plane, this would be something that's there. Like it's -1 to 3. Maybe the graph looks something like this with a closed circle, and this line is connected because I'm including every x, every domain that's between -1 and 3. That's why it's connected. Types of data that are continuous. Time is always continuous. Distance can be continuous. Time is continuous because I can get, if I'm looking at how tall a plant's growing over the course of months, I can look at it at maybe 1.2 months and get a height on that plant. I can look at it at 1.25 months and get a different height. It's continuous. It includes everything between. Hopefully that helps.